at an incredibly noisy, crowded cocktail party.
Okay.
You are a token, and your word is mole. Now, the word mole, standing completely alone in a room, is terrified and confused. It has no idea what it is. Is it a furry little animal digging up a garden? Is it a dark blemish on someone's skin? Or is it a chemical measurement in a high school science class?
The isolated token lacks semantic grounding.
Right. So the word mole shouts out a query into the cocktail party. It says, I'm looking for context. It scans the rim of the sentence, looking at the keys held by all the other words.
I see where you're going.
Over by the punch bowl, it sees the word garden holding up a key. Over by the door, it sees the word dirt holding up a key.
And this is where the math happens. The model calculates an attention score by taking the mathematical dot product of the mole query and the garden and dirt keys.
The dot product.
Yeah, the dot product basically measures alignment in vector space. Because they align highly, the score skyrockets.
And because the score is high, mole pulls in the values from garden and dirt. It absorbs their context, and in a flash of realization, it says, I am an animal.
That is a phenomenal way to visualize it. And the magic of the transformer architecture is that it does this in parallel.
At the same time.
Right. Older architectures, like recurrent neural networks, had to read a sentence sequentially, word by word by word. It was agonizingly slow. Transformers use multi-head attention to let every single word in the sentence shout its query and check every other word's key simultaneously.
But as you mentioned earlier, checking every word against every other word creates a quadratic scaling problem. If the sentence is 10 words long, that's 100 checks. If it's 1,000 words long, that's 1,000,000 checks. The architecture had to be optimized to handle the massive context windows we see today.
Absolutely. The 2025 and 2026 literature focuses heavily on 3 architectural enablers that solve these bottlenecks. Let's begin with ropey rotary positional embeddings.
Because if a transformer reads the whole sentence simultaneously in parallel, it loses the order of the words. Like, the dog bit the man looks mathematically identical to the man bit the dog, unless you explicitly tell it the positions.
Exactly. In the original 2017 paper, they solved this by simply adding a static mathematical wave, a sine wave, to the word's vector to indicate its position.
To stick in a number on it.
Basically. But static addition is fragile over long distances. Rope-E revolutionized this. Instead of adding a static number, Rope-E applies a complex space rotation matrix to the token's representation.
A rotation matrix. Let's break that down, because that sounds intense.
It's actually pretty intuitive. Think of a clock face. If a word is at position 1 in the sentence, maybe its vector points to 1 o'clock. If it's at position 3, the matrix rotates the vector to point to 3 o'clock.
Oh.
Yeah. By encoding position as an angle of rotation rather than a static additive value, the model can mathematically deduce the relative distance between any 2 words just by looking at the difference in their angles.
So angle instead of position. That's deeply elegant. And this relative measurement is what allows modern models to process 32,000 or even 100,000 tokens of context gracefully.
Precisely.
Okay, the second major architectural update the sources highlight is GQA grouped query attention. And from my reading, this seems purely born out of a desperate need to save RAM on the graphics cards.
It is entirely an optimization for inference. The phase where the user is actually generating text.
Right.
In standard multi-head attention, every single query head gets its own dedicated key and value head. But generating text is an autoregressive process. You generate one word, then you have to feed that word back in to generate the next word over and over.
It's like laying train tracks directly in front of a moving train.
Exactly. And to prevent the model from recalculating the entire history of the sentence every single time it moves forward, it stores all the previous keys and values in memory. This is called the KV cache.
But as your context grows...
That KV cache swells massively, eating up all your GPU memory bandwidth.
So how does GQA fix the cache bloat?
By enforcing sharing. Instead of giving every query its own key and value, GQA groups multiple query heads together and forces them to share a single key and value representation.
Oh, wow.
Yeah, it mathematically compresses the KV cache required, drastically reducing memory consumption during generation. And what's incredible is that the empirical results show this massive compression results in almost zero loss in actual model intelligence.
That's wild. It's like having one really efficient librarian serving 5 different researchers at once. Instead of paying for 5 separate librarians, you save a fortune and the books still get found.
Exactly. And the final pieces of the architectural puzzle mentioned in the reports are SWIGLU and RMS norm. These deal with the internal plumbing of the neural network layers.
The activation functions and normalization. I find activation functions fascinating because they are basically the gates that decide if a neuron fires or not.
They introduce nonlinearity.
Hmm.
Without an activation function, a neural network is just a series of linear multiplications, which would mean it could only ever understand perfectly linear relationships.
And the world is nonlinear.
Very much so. SWIGLU replaces older functions like ReLU or GLU. It acts as a sophisticated gating mechanism that multiplies the input by a sigmoid-like curve, which empirical evidence from 2025 shows provides much smoother gradients during the backward pass of training.
It basically prevents neurons from dying and ceasing to learn.
Exactly. And then there's RMS norm root mean square normalization.
Right, because neural networks are highly sensitive to the scale of the numbers passing through them.
Very sensitive. If the numbers get too large, the network explodes mathematically. If they get too small, it vanishes. Normalization forces the numbers back into a stable range.
How does it do that?
Well, older methods, like layer norm, used to calculate the mean of all the numbers and subtract it to center everything exactly at 0 before scaling them. RMS norm skips the centering step entirely. It only scales the numbers based on their root mean square.
Wait, if centering the mean is computationally heavy and RMS norm just skips it, doesn't the model lose stability?
That was the initial fear. But the math proved otherwise. Skipping the mean centering saves significant computational overhead, and the network remains perfectly stable during training. It is a pure efficiency win.
Incredible. So we have this highly optimized transformer engine. We have our BPE tokenized fuel. But an engine is nothing without a massive reservoir of that fuel. And that brings us to the brute force reality of pre-training and the looming data wall. What exactly are we pouring into this machine?
The scale is almost difficult for the human brain to comprehend. We are talking about 1 to 4 trillion tokens for a standard base model.
Trillions.
Yes. This data is usually derived from colossal scrapes of the entire public internet from organizations like Common Crawl.
And the goal during this pre-training phase is incredibly, almost frustratingly simple.
It is entirely singular, causal language modeling. Given a sequence of tokens, predict the very next token. That is it. There is no higher order goal.
Let me make sure I have the mechanics of this right, because this is where the loss function comes in. The model is just guessing the next word.
Right. The model outputs a probability distribution over its entire vocabulary, say 100,000 tokens. It assigns a percentage to every single word. Like, I'm 80% sure the next word is cat, 10% sure it's dog, and 0.801% sure it's refrigerator.
And then we check the actual training data. If the word was indeed cat, what happens?
We use a metric called cross-entropy loss. It measures the divergence between the model's predicted probabilities and the actual truth.
Going back to the mountain analogy.
Exactly. If the model was highly confident and correct, the penalty, the loss is tiny. The mountain valley is very shallow. But if the model was 99% confident the word was refrigerator and the actual word was cat, the cross-entropy loss explodes.
A massive penalty.
It is a massive penalty.
Yeah.
The model uses gradient descent to backpropagate that massive penalty through its billions of weights, adjusting them so that next time it doesn't guess refrigerator.
It's like playing hangman, but you get violently penalized for being confidently wrong. And by repeating that simple prediction game trillions of times, the model is inadvertently forced to learn grammar, historical facts, logical reasoning patterns, and even computer code structure, simply because understanding those things makes it statistically better at predicting the next word.
The capabilities emerge as a byproduct of the prediction compression. But as you can imagine, you cannot just shovel the raw internet into this prediction engine. The public internet is a toxic swamp.
Oh, it's awful. It is full of SEO spam, broken boilerplate HTML code, completely corrupted text files, and horrendous human toxicity.
Which necessitates a rigorous multi-tiered data filtering pipeline before training even begins.
What's the first step?
The first step is simple language IDE, classifying the text and dropping documents that aren't in the model's target language distribution. But the second tier is heuristic pruning.
Heuristic pruning, what does that actually look like in the server room?
It relies on statistical, rule-based filtering. You scan a document. If it has an average line length of 150 characters but absolutely no spaces, it is probably broken code or a data dump, not natural language. It gets dropped.
Makes sense.
If it has a massive ratio of symbols, like a page that is just 1,000 hashtags or ellipses, it gets dropped. If a single word is repeated 50 times in a row, it's spam. Dropped.
So it's basically sweeping out the obvious garbage. But what fascinated me most in the technical reports was the deduplication phase. The sources talk about using min-hash and locality-sensitive hashing.
Deduplication is arguably the most critical step for model generalization. The internet is highly repetitive. Think of how many times the standard MIT open source license text appears on GitHub.
Millions of times, probably.
Right, millions. If a model sees the exact same paragraph 10,000 times during training, gradient descent will over-optimize for that specific sequence. The model will just memorize it verbatim rather than learning general language rules.
It's like a student just memorizing the answer key to a test instead of actually learning the math formula.
Precisely. So they use min-hash algorithms, which create lightweight statistical fingerprints of documents. If two documents have nearly identical fingerprints, they're clustered together, and the pipeline throws away all but one representative instance. You preserve the knowledge, but remove the repetition.
But the 2025 pipeline goes even deeper than exact text matches, doesn't it? The sources detail semantic diversification.
This is a remarkable modern technique. Sometimes text isn't a direct copy-paste, but it is semantically identical. Imagine thousands of corporate marketing pitches. They use slightly different words, but they convey the exact same low-value information.
So how do you filter that if the words don't explicitly match?
They use smaller, pre-trained embedding models to translate the documents into vector space. They plot them on a massive multidimensional map.
Okay, a big map of concepts.
Exactly. If thousands of documents are clumped tightly together in that space, it means the data set is overly saturated with that specific semantic concept. The pipeline deliberately prunes that dense cluster, and inversely, it upsamples documents that sit in rare, isolated, high-information regions of the map.
I have to challenge this logic for a second, though. The entire premise of the large language model boom since 2020 has been more data is better. If we have an equation where n is the number of parameters and d is the volume of data, why are we intentionally throwing so much of the d away? Wouldn't we want the model to see everything?
It is a phenomenal question, and the empirical evidence from 2025 and 2026 provides a definitive answer. Token quality fundamentally matters more than raw token volume.
Really?
Yes, the labs discovered that repeating highly filtered, exquisitely pure data sets for multiple epochs, meaning running the model through the exact same brilliant data 10 times, actually produces a smarter model than a single pass over a massive dirty data set.
Quality over quantity, mathematically proven at scale. Let's dig into the math of that scaling, actually, the famous formula. Compute approximately equals 6 times parameters times data, C equals 6ND.
Yes. Back in 2022, DeepMind published the Chinchilla scaling laws. They mathematically proved that most models at the time were terribly undertrained.
What did Chinchilla argue?
Chinchilla argued that if you have a fixed compute budget, say you only have a certain number of GPUs in a certain number of weeks, you should scale your parameter count and your token count equally.
And what did that equal ratio look like in practice?
It worked out to roughly 20 training tokens for every single parameter in your model. If you had a 10 billion parameter model, you should train it on 200 billion tokens to be perfectly compute optimal.